We are in section 8.2, area of surface of revolution. A surface of revolution is formed when a curve is rotated about a line. Such a surface is the lateral boundary of a solid of revolution of types discussed in 6.2 and section 6.3. Recall that the surface area of a cone is area equals pi times r times L. So r is going to be our radius, and L is going to be the slant height. In this section, we're going to take a frustum, a portion of a cone, to calculate the surface area of the curve. So in order to do this, we have a picture here we're going to kind of look at. And so what we're going to do is we're going to call the bottom radius down here R2 of the larger cone. And then you can see the smaller cone up here, we'll call the other radius R1. Likewise, I'm going to call this smaller slant length L1. And then we'll call the remaining part of the slant height of the larger cone L. So our area, and what we're looking at is the area of this part in here. So we're going to do the larger cone minus that smaller cone to get that area. And so we're going to have pi r squared for the larger cone. And then the slant height for this is going to be L1 plus L minus the area of the smaller cone, which is pi R1 L1. And so we're going to rewrite this. I'm able to write this as pi. And then we have R2 minus R1 times L1, since they're both being multiplied by an L1, plus we also have pi R2L. And so we're going to explore the part that's written right here. And so in order to do that, I'm going to think about similar triangles. And so I'm going to go ahead and look at L1 over R1 for the smaller cone, or smaller triangle if you want to think of it like that. And then for the larger one, that slant length is going to be L1 plus L all over R2. Cross multiplying here, we have R2 times L1 equals R1 times L1 plus R1 times L. And then moving both of these terms that have the L1 to the same side. This is going to be the same thing as R2 minus R1 times L1 equals R1L. And so if you look at what we have underlined over here, R2 minus R1 L1 is exactly what we have written over here. And that is equal to R1L. So I'm going to go ahead and replace that. So this is going to be the same thing as pi times R1L plus pi times R2L. From here you can factor out a pi, and I'm going to go ahead and say R1 plus R2, and you can also factor out that L. So from here I'm going to rewrite this just a little bit different. So I'm going to multiply by a 2 and also multiply by a 1/2, and we'll say 1/2 R1 plus R2 times L. So we can say that thus the area of the frustum of a cone is A equals, and I'm going to go ahead and put 2 pi times R, and I'm going to define R as 1/2 R1 plus R2 times L, and we'll say where R equals 1/2 R1 plus R2. Using the concept of arc length, we can find the surface area of f of x about either the x-axis or the y-axis. So down below, it says, first box says let f be positive and have a continuous derivative, Then the surface area of the surface obtained by rotating the curve y equals f of x with x between a and b about the x-axis is, and so in order to do this, taking our curve, which is s equals the integral from a to b of, and we're going to have 2 pi y, which y would be our radius, and you can see that down below. So in our picture here, y is our radius. So radius equals y. And so we have 2 pi y times that length that we have. And that length is found by what we did in the last section, which is 1 plus the derivative squared, and then dx, since we're rotating it about the x-axis. So another way to think about it is that s is equal the integral from a to b of 2 pi r, or in this case r is y, so our radius again is y, and ds, where ds is equal to that length of that curve, so 1 plus the derivative squared dx. Right next to that, it says let g be a positive function and have a continuous derivative also. Then the surface area of the surface obtained by rotating the curve x equals g of y between y values between c and d about the y-axis. This time, and I know it's a little difficult to see here, but the radius is on here. So this time our radius is equal to x, since that's that distance down here. So this is x versus over here in the first one, that was the distance of y. And so our graph, our surface area is going to be s equals, and it's going to be the integral from c to d, 2 pi radius, the radius in this problem is x, times that length of that curve, which is going to be 1 plus g prime of y squared dy. Or again, rewriting it, it could be the integral from c to d of 2 pi x ds, where ds this time is going to be equal to that length, which is now defined as 1 plus g prime of y squared dy. The example on the next page says find the exact area of the surface obtained by rotating the curve about the x-axis. So it tells us about the x-axis here, and we're looking for the surface area of this. And so the function that we have for part A is x equals 1 plus 2y squared, where y is in between 1 and 2. And again, note these are your y values. And so in order to do this, I'm going to go ahead and sketch what it is that we have here for our curve. And so going ahead and looking at this, and we are rotating this about our x, so I need to keep that in mind. But for this, the y values that we have are between 1 and 2. And I'm going to go ahead and go out, we'll say 10 spaces on our x. So first of all, when our y value is 1, if you plug that in, you get an x value of 3. And then when y is 2, you get 4 times 2, which is 8, plus 1 is 9. And so our curve here is that x equals 1 plus 2y squared. And we're going to take this and we're going to rotate it about the x-axis. So if you think about it being reflected down here, I'll just do a rough sketch. And as it rotates around, that is what we're going to end up with. And if you notice the radius here, this would be r. And r in this problem is equal to, so our radius is equal to y. So that's a y value. And so in order to calculate the surface area, we need to write down our formula, which is going to be the integral of, and the way that this is written would be 2 pi y times the square root of 1 plus f prime of y squared dy. And so taking the derivative, we need to get what f prime of y is. So calculating the derivative with respect to y, this is the same thing as dx dy. And our derivative is just going to be 4y if you take the derivative of 1 plus 2y squared. And so setting up the problem, we would have the integral from, and the values that we're going to be integrating, we're integrating with respect to y. So we're going to be going from, it tells us from 1 to 2, of 2 pi y times the square root of 1 plus the derivative squared, and we just calculated the derivative to be 4y. So 4y squared dy. From here, we can simplify this a little bit. The 2 pi you can pull out in front of your integral. So we say from 1 to 2 of y times the square root of 1 plus 16y squared dy. And we can't integrate it as it is right now, but we can use a u sub. So we'll let u equal 1 plus 16y squared du is going to be equal to 32y dy. And so now our problem is going to become, it's going to have the 2 pi, but this time we're going to divide by the 32 also. I need to change my limits of integration. And then I'm going to have the square root of u, or just u to the 1/2 du. And now your new upper limit of integration is going to be 1 plus 16 times 2 squared. And your new lower limit is going to be 1 plus 16 times 1 squared. So new lower limit is 17. That new upper limit works out to be 65. So from here, we get pi over 16, simplifying that, times u to the 3 over 2 times 2 over 3 out in front, evaluated from u equals 17 to 65. So pi over 16 times 2/3 simplifies to being pi over 24. And then substituting in 65, we have 65 to the 3 over 2 minus 17 to the 3 over 2. And this is a perfect answer. If you wanted to rewrite it a little bit, you can, and say this is going to be 65 times the square root of 65 minus 17 times the square root of 17. Either answer that is written is fine. And again, this gives us the area of that surface, the surface area obtained by taking the curve x equals 1 plus 2y squared between 1 and 2 y values and rotating about the x-axis. So there's another example right below this that I'm going to go ahead and circle that we'll look at together in class. And on the next problem, it says the given curve is rotated about the y-axis. So this time we're rotating it about the y-axis, whereas the other two examples are rotating about the x. So this time it says sketch the graph and find the area of the resulting surface area. So sketching this curve, note that it is bounded by y between 0 and 1 and x between 0 and 1. And we're rotating about our y-axis. So we're just going to be going up to 1 and out to 1 here. And if you were to graph this, pick some values to plug in and kind of see the curvature here, but I'll sketch it here for us. And we're going to rotate this about the y-axis. So as that rotates, it's going to look something, reflect and be something like this. And so as you rotate this, that radius is going to be here. So here's our radius. And the radius in this problem is going to be equal to x. So you can see that it's an x value, and it changes depending on that function. That's why it's a variable. So in order to do this, our formula is s equals the integral of 2 pi x, since that's our radius, times the square root of 1 plus f prime of x squared dx. And since we're dealing with x as our variable and integrate with respect to x, that means that I need to put down the x values here of 0 to 1. In order to take this derivative, I need to first isolate y. And so doing that, if you were to get y by itself, you would have y to the 2/3 equals 1 minus x to the 2/3. So y is equal to 1 minus x to the 2/3 raised to the 3/2. And now that we have that to take our derivative, so we'll say dy dx, or f prime, is equal to, and you're going to put 3/2 times 1 minus x to the 2/3 raised to the 1/2 power. So times, and then taking the derivative of the inside, you're going to end up with negative 2/3 x to the negative 1/3. And so you can simplify this a little bit. First note that the 3/2 and the 2/3 are going to cancel out, reduce out. And then this is going to simplify that. X to the 1/3 will move to the denominator. And so this would be 1 minus x to the 2/3, the square root of that, over x to the 1/3. And so our surface area formula is going to be the integral from 0 to 1 of 2 pi x times the square root of 1 plus, and then our derivative, which is equal to negative the square root of 1 minus x to the 2/3 all over x to the 1/3 squared. So in doing this, we are also integrating with respect to x, so make sure you put your dx. From here, you can pull the 2 pi out in front of your integral. So we have x, so we can simplify our radical. So we have 1 plus, squaring this, the negative will turn positive, and then the numerator is just going to be the 1 minus x to the 2/3. All over, and then the denominator is x to the 1/3, so squaring that's going to be x to the 2/3 dx. Then you can separate this and look at each of these terms over the denominator. So we have 2 pi times the integral from 0 to 1 of x, square root of 1 plus, and so we're going to end up with 1 over x to the 2/3 minus 1 dx. And so now looking at this a little bit more, those ones are going to reduce out. And so I have 2 pi times the integral from 0 to 1 of x times the square root of x to the negative 2/3 dx. And the square root's the same as a 1/2. So this would be 2 pi times the integral from 0 to 1 of x. And so this is going to be the same thing as x to the negative 2/3 to the 1/2 power dx. And from algebra, we know that you would multiply those exponents together. So still going through this algebra, we have the equals 2 pi from 0 to 1 of x times, and so 2/3 times 1/2, and it's negative, is going to become x to the negative 1/3 dx. Again, using our exponent rules, you can combine those two exponents. And so we get 2 pi times the integral from 0 to 1 of x to the 2/3 dx. We are able to integrate this using our power rule. So we have 2 pi times, it's going to become x to the 5/3 times 3/5. And we're evaluating this from x equals 0 to 1. Simplifying what we have out in front, we get 6 pi over 5. And then we're going to evaluate this from 1 to 0. So plugging in 1, you have 1 to the 5/3, which is just 1 minus 0. So this works out to being 6 pi over 5. So we have another example here that I'm going to go ahead and circle, and we'll work on this one together in class.